So let's finish off the last vestiges of nomenclature of alkenes and alkynes. And we had covered most of it in the previous lecture. Really, we had looked at the UPAC linear alkene nomenclature and alkyne nomenclature. Here's an example with an alkyne. And we had ended with this UPAC cycloalkene nomenclature. There was some little idiosyncrasies specific to that, which were different than the nomenclature of linear alkenes, and we showed the difference between them. So now we're going to go back and revisit something that we looked at in the last lecture, which is going to have an important bearing on actual nomenclature. So alkenes, as we had noticed before, or had mentioned before in the last lecture, there cannot be free rotation around carbon-carbon double bonds, only around carbon-carbon single bonds. So we see on these two structures here on the left and the right, we cannot interconvert between these forms because we cannot rotate around these carbon-carbon double bonds, because notice if we were able to, we have a couple of substituents here. This R group, which could be these R groups could be a substituent or just a continuation of a parent chain. Here we have them on the left-hand side on opposite sides of the double bond, whereas these R groups here now are on the same side of that double bond. Again, these R groups could be the continuation of a parent chain. They could be substituents like chloro or bromo or something like that. But the point is that we cannot interconvert between the two forms. So thus they are different compounds. They're completely different compounds. So they have to have different names, and that can now be an issue. This is very similar to when we were looking at cycloalkanes, all carbon-carbon single bond, but they were locked into a cyclic structure, in which the free rotation now around the carbon-carbon single bonds, we were not able to do that. So we had come up with a sort of terminology to describe them as either cis or trans. They were related to each other as geometric isomers. Alkenes can also be related as geometric isomers, having the same molecular formula, the same connectivity, but different orientations of either the parent structure or substituents in space. Whenever we have the term geometric isomers, that means we're going to be putting the term cis or trans on that, somewhere on that name. A good case in point would be our 4-carbon alkene, that of a butene. If it's 4 carbons, it's but. If it's got a double bond, it's ene, butenes. And if we number both of these, they each have 4 carbons, and we have a double bond between the 2 and the 3 carbons. So in both cases, this would be named 2-butene. But this is a problem now because we cannot interconvert between the two. So thus, we have 2 different compounds. But at least so far, we have 2 identical names, and we cannot have that. So let's look at this in more detail. Here's where we left off. We had 2 structures, 2 different structures, different compounds that had the same name. So we said these were going to be related as geometric isomers. Whenever we hear the term geometric isomers, we're thinking, okay, we're going to have to put a cis or a trans on the name. When we were looking at geometric isomers of cycloalkanes, well, if they had 2 substituents on there, one was on one side of the ring and one pointed to the other side of the ring, that was trans. Or if our 2 substituents pointed to the same side of the ring, that was a cis geometric isomer. Well, the same can be said for alkenes. We just look at them a little differently when we're trying to discern whether they are cis or trans. And the key here is to put a line, if you will, or draw a line in your mind. I'm going to draw one right here, but going across that double bond. Now, if we look at the structure over on the left, we see that the parent chain in this butene butene, extends to either side of the double bond. One could say it is transposed with respect to its where these things are on either side of the double bond. So this would actually be considered a trans 2-butene, because those two, the continuations of the parent structure are on one side of that dotted line and the other side. So that would be trans 2-butene. Looking over at the structure on the right, well, we've drawn that dotted line there through that double bond, and we notice that the rest of that parent structure is on the same side of that double bond. So therefore, if that's the case, they're on the same side of the double bond, this has to be cis 2-butene. Now we're finally getting somewhere. We have two different compounds, now finally two different names. So knowing this, we are going to keep this in mind as we start to name some representative alkenes. So we have two problems to solve here. Oh, the one on the left is a structure. We're going to be asking for a name. The one on the right is a name. We're going to have to draw its structure. We're still within the realm of geometric isomers of alkenes, so we will have to address that at some point. Let's look at the structure over on the left. Longest continuous carbon chain containing that multiple bond. Well, if we look at that, we draw this here, and we can count the carbons, and there's 8 of them, and it turns out to be octene. Why oct? Because oct is 8. Ene, because there is an alkene within there. It is an octene. Now we have to number this parent structure such that the first carbon of the multiple bond encountered has the lowest numerical designation. I would hope you could see, in looking at this, it's like, well, that double bond seems to be pushed over to the left-hand side of the molecule, and it is. So you wouldn't have to count both ways, and if you didn't want to, you could kind of make a guess and say, all right, I'm going to start counting over on the left-hand side. And I find that, having done that, counting 1 through 8 carbons, that double bond starts at carbon 3. So thus, that is a 3-octene. So remember, we always do this nomenclature starting at the back and moving to the front. Fair enough. So let's take a breather here, a timeout, and look at that parent structure. If we look at that parent structure, I'm going to draw an invisible line, if you will, through that double bond. That's not very well done, but we can see that the parent structure goes on one side and the other side. It extends to both sides of that double bond. So this is, by definition, going to be a trans name on here. So we know trans is going to be in the name. So that always goes up front. So I've just front loaded that. Lastly, we have to look at our substituents, and we have a methyl group and an ethyl group. Again, we would go with the ethyl first because E in ethyl comes before M in methyl, noticing what carbons that ethyl and methyl are attached to, and we number them thusly. And this would come out as trans 5-ethyl 3-methyl 3-octene. Again, quite a mouthful. And again, you sort of start wondering, how did I come up with this name? This is so complex. You start to doubt yourself. And the reason why you can do that is you take it in manageable chunks, one step at a time, typically starting at the back and moving towards the front. That's what UPAC nomenclature is great for, that because once you get an understanding of those rules and the succession they are in, you have a very powerful tool at your control. Okay, let's look over at the structure on the right. We start at the back. Remember, if we start at the back, we see that we have a hexene. Hex is 6. Ene means there's an alkene in it, and it starts at that 3 carbon. So that's great. I can just draw that parent structure right now, can't I? And there it is. And I get 1, 2, 3, 4, 5, 6. Right at that 3 carbon, we have the start of that double bond ending at the 4 carbon. Wow, this seems very easy, doesn't it? Let's be a little careful, shall we? Because let's look over on the front of this name, and we have the word cis. Is this a cis double bond as drawn? If we draw a imaginary line down that double bond, No, that parent structure extends to either side of that imaginary line. So that what we've done is actually drawn a trans. So we have to start again and carefully now draw a cis parent structure. And if we look at what we have here, I've drawn 8 carbons, and I will number those 8 carbons and put a double bond between the 3 and the 4 carbons. So now I have a cis 3-hexene. The only thing left is to look at we have on the 2 carbon here, we have a fluoro group. And on that fluoro, so if we just draw a fluoro group in there, we have finished this structure. Always important to be cognizant of when going name to structure, give it another look because it might be cis. So as frequently happens in certain nomenclature instances, sometimes we encounter exceptions. And we're going to note some exceptions in the nomenclature of alkenes when cis and trans is not used. When cis and trans is not used. So this is exceptions to when cis and trans is used. So that would mean it's not utilized. And the first one we're going to be looking at is when we are tasked with naming a terminal alkene. A terminal alkene essentially just means that we have an alkene whose parent structure, the carbon-carbon double bond, is on the end of the parent structure. In this case right here, we see that that is the parent structure, the longest continuous carbon chain which contains that double bond. Well, that alkene is on the end. So we're going to keep in the back of our heads here, we're not going to be using cis trans in this nomenclature system. So we would find that in this parent structure, it is 7 carbons, and thus that is a heptene, hept for 7, ene because it's an alkene, and we're going to number it such that, and this is a slam dunk, we know which way we're going to number it because the first carbon of the multiple bond must have the lowest numerical designation, in this case 1. So this would be known as a 1-heptene. Fair enough. Now all that's left to do is to identify our substituents. I see a methyl at the 2 position and a bromo at the 4 position. So bromo, the B in bromo, comes before M in methyl, and we would name this 4-bromo, 2-methyl, 1-heptene. Importantly, because we have a terminal alkene as the parent structure, no cis trans would be in the name. If you put cis or trans in the name, it would be a wrong name. So just keep that in mind. The second time when cis or trans is not used in alkene nomenclature is when we have an alkenes on either carbon if they have identical carbon architecture. So let's look at this structure below. Is this a case where we have identical carbon architecture on either of the double bond carbons? Well, let's first identify the double bond carbons. I see one here in this line structure, and I see one here in this line structure. Now let's look at the carbon over on the right first. Well, I see we have a whole lot of this sort of carbon shrubbery over here, and not written in here is actually a hydrogen. I'm going to draw this very crudely right here just to show you. Coming off of that carbon, we have the hydrogen and something else other than a hydrogen. So clearly there is not identical architecture on that carbon. But now let's look at the carbon on that structure over on the left-hand side. Well, I see here we have essentially a 2-carbon ethyl structure and another 2-carbon ethyl structure. In this case, we have identical architecture off of the same carbon, one of the carbons on that alkenes. Notice it has to be off the same carbon. Identical architecture. Thus, we're going to keep in the back of our head the fact that we are not going to be putting either cis or trans on this alkene nomenclature. But we still have to name it. So let's go and find the longest continuous carbon chain holding that double bond. And indeed, this would be the way to go on this. Note that I could have made this parent structure starting down over on the right, or left, I'm sorry, here. That could have been my parent structure, and it would have given the same answer. Why? Because we have identical architecture on either side. Fair enough. So we have our parent structure working out here, and we find that once we count the carbons, well, there are 8 of them. And so we have an octene, again, starting back, moving to the front. Well, we have to number this such that the first carbon in the multiple bond gets the lowest numerical designation. You could try both ways. I look at this and see, well, that double bond seems squished over to the left-hand side, and you'd be right. So there's the numbering right there. And we find that that octene, that double bond, starts at the 3 carbon on this numbering. So 3 octene. Lastly, we find, well, what are our substituents now? Well, I have a couple of ethyl groups. Ethyl at the 3 carbon, ethyl at the 5 carbon. And we finish this off by putting this as a diethyl with 3 and 5 in there. 3,5-diethyl, 3-octene. It is an alkene. We have named that alkene, but there is no cis and trans terminology in there because, as we saw before, off of one of those carbons, we had identical architecture. When we have that, no cis trans. So we'll just clean up some last vestiges of this geometric isomerism in multiple bonded species. Firstly, with alkynes, is it possible to, that's carbon-carbon triple bonded species, and is it possible to have a cis and trans geometric isomerism for alkynes? Well, no. Alkynes are linear and only have one substituent per carbon on the triple bond, so they can never exhibit geometric isomerism. Remember, on our alkenes, we had, if this were an alkene, there was substituents or 2 substituents on each carbon, so we could discern between cis and trans. There's only 1 per carbon on an alkyne, so the short answer here is that alkynes never have geometric isomerism or cis and trans associated with them. Lastly, and this is something we touched on in the last lecture, smaller cycloalkanes are only possible as the cis geometric isomer. Cycloalkanes, at least the ones that we deal with, we have a very nice cis double bond here, and it fits nicely into a cyclic structure. As such, we never put the term cis in naming cycloalkenes because trans cycloalkenes, at least on the carbon numbers that we're working with, are far too strained to exist. You could not make this. If you tried to make this trans cyclohexene with a model kit, you would break your model, you'd snap your models. It's just not possible to do. So thus, we would not be able to, since only a cis is available, we don't even bother to put the cis in there. It would just be cyclohexene, not, for instance, cis cyclohexene is the way this would go. So this is only cyclohexene, not cis cyclohexene. So there's many ways that we could be approached with this alkene terminology, specifically or notably nomenclature. We've done a number of examples of structure to name to structures. Sometimes they can have sort of a way of looking at it or an approach to a problem, something like this. Well, we have a number of pairs here. Identify the pairs of identical compounds. This is sort of a build on something we've done previously, and identify the pairs of geometric isomers. Well, if we parse through this, if we look at that the center pair right there, we would immediately be able to see that these are identical compounds because these dashes and wedges right here, it doesn't matter because this is a linear structure, and because we have free rotation around the carbon-carbon single bonds, one can easily turn into the others. So these are examples of identical compounds, are the ones that we see, both of them, over on the right-hand side. And in fact, we had looked at these before already as examples. I've just thrown in a couple of new ones, in which now, if we named these pairs, we would find that they would have the same name. On the top and on the bottom, we would come up with the same UPAC nomenclature. This is a great way to determine whether we're dealing with identical compounds or are they related in another way. And we have some constitutional isomers over on the left-hand side. If we named these, one would be 2-methylpentane and one would be 3-methylpentane, and they are related as constitutional isomers because they have identical chemical formulas but different connectivity. The last one is sort of a gimme because they're a pair of alkenes already. And we find that these are indeed geometric isomers. You might think initially, well, are these identical compounds? And well, we'd have to be careful here. We'd have to put, all right, let's put a line down the double bond on both of these, like we have here. And what is the parent structure? The longest continuous carbon chain on this one would be the one in which the parent structure goes on both sides of the double bond. And the other one, well, that has the parent structure emitting itself on the same side of the double bond. One would be cis, one would be trans, but they would indeed be geometric isomers. So finally, we're going to do some chemistry. That's what we're here for, chemical reactions. And we're going to find that with alkenes and alkynes, they primarily have one type of reaction, if you will. We're going to have a number of reactions because alkenes and alkynes are much more reactive than alkanes, but it's of one type. And this type is known as addition reactions of alkenes and alkynes. Addition. Remember, for alkanes, we had substitution reactions, where I take a little bit of one piece and put it over on the reagent piece goes over and comes to the starting material. Always, again, we are dealing with a functional group interconversion. We start with one functional group, and we end with another functional group. But it is considered an addition reaction. So there's two types of ideas we have to look at, two ideas for addition reactions. And we can look at this structure down on the bottom here, where we have our alkene or alkyne starting material. We have a reagent, as we saw before. Over the arrow, we have conditions or not. Some of these reactions are spontaneous. And then we have our product. So it fits the bill that we saw before of an organic type transformation, drawing pictures, if you remember. The first thing to look at is that our reagent is added over that carbon-carbon multiple bond. So with this reagent, we have one component of the reagent which is added to one carbon of the multiple bond, and another component of the reagent which is added, meaning covalently bonded, to the other one. That double bond that we see right here is converted in the product to a single bond. Double bond to a single bond. But notice in our product profile that one side of this reagent is attached to one carbon, and the other part of the reagent is attached to the other carbon. They have to be on adjacent carbons. Now, looking specifically at that reagent, I've given it as A and B. Basically, the identities of A and B, is it a hydrogen, is it a chlorine, is it a methyl or whatever, the identities of A and B on each reagents vary when we look at different actual reactions, but they're all considered addition reactions because they follow the same idea. They're always connected by a single covalent bond to adjacent carbons in our product. So we're going to look at a number of these as we move forward. The first one we want to look at looks at a reagent which is considered symmetrical. The first couple of reactions we're going to look at are considered the reagents we use are considered symmetrical reagents because whatever A is, so is B. If A is a hydrogen, B is a hydrogen. If A is a chlorine, B is a chlorine. They're identical. It's a symmetrical reagent. Let's look at the first example, reaction that is an addition reaction. Hydrogenation of an alkene or an alkyne, given in a very general sense here. We start with an alkene, and the name of the reaction, it gives a hint as to what the reagent is. What might be the reagent from hydrogenation? Possibly hydrogen, or if you like, hydrogen, and indeed it is. Hydrogen is our reagent. It is a symmetrical reagent because it has a hydrogen on one end of the covalent bond and on the other end of the covalent bond. Why? Because hydrogen is a diatomic element. It must be so. So therefore, this is indeed diatomic hydrogen is used as the reagent. And in fact, a vast excess of hydrogen is used. Now, so that we've covered the reagent in hydrogenation, it is hydrogen. Over and indeed under the arrow here are the conditions of our reaction. And we find that the conditions, we have a catalyst, a metal catalyst as one of the conditions. And it is either nickel, palladium, or platinum. It requires one of these three metals as a catalyst. So you'd say like catalytic PT or catalytic PD or Ni would be over the arrow. Underneath the arrow, we have here pressure, which means since we have a whole lot of this hydrogen, which is a gas, we can really put that excess in there under a high degree of pressure. So once these conditions are met, we have an excess of our H2 reagent. And notice, just as an aside, I've drawn this suggestively. Normally we just draw H2. But I've drawn this with the covalent bond to show that we're trying to draw this suggestively to show that, all right, well, this carbon is going to have a covalent bond with that hydrogen in the end. This carbon is going to have a covalent bond with that hydrogen in the end, and that double bond is going to go down to a single bond. And indeed, that is what we see in our product, an addition reaction. Our functional group interconversion is an alkene being converted to an alkane. An alkene to an alkane. Remember, there's always a functional group interconversion that we can identify in these examples. So let's take a look at some actual examples as we move forward. Here we are. We're going to play your favorite game and mine again, What's in the Box? So here we have to sort of be a sleuth again, piece together our reagents, our conditions, and so forth, and be able to sort of zero in on what reaction is going on here. Because by the end of the course, you're going to have a very large repertoire of reactions. And when we're playing What's in the Box, we very quickly have to cast away or exclude different reactions until we settle on, okay, this is the particular reaction that we're going to be doing. So let's look at what we have here. We have an alkene, happens to be a cycloalkene over on the left-hand side here, but it's an alkene, and we have an excess of hydrogen. Oh, well, this is going to be a hydrogenation. Slam dunk, absolutely. And we can be even more sure because we have one of our three metals here over the arrow. A hydrogenation is the only one that will have a metal as a condition of the reaction, a metal catalyst, so that's a slam dunk. And we have pressure, gas pressure, namely that hydrogen pressure in there. So all this we have to understand moving forward. So how we would look at this, and I've drawn this an initial alkene over on the left in line drawing, but let me sort of enunciate the two carbons that matter by actually putting those carbon atoms in there and the hydrogen atoms, which are assumed to be covalently bonded to them. So what would happen here? Well, if I had my, let's draw a couple of hydrogens here, and I'll draw that suggestively before H, covalent bond H, that HH, if you will, is going to lie right down on that double bond, converting it to a single bond. And indeed, that is what we would end up with. Really, you could draw it like this. We've gone from an alkene to an alkane. However, if you could very easily just sort of track back to line drawing and put in that box the structure in line drawing. So clearly, we went from our alkene to our alkane. Really, we just got rid of the double bond. That's what a hydrogenation does, whether it's a double bond or a triple bond or whatever. All right, so here's another one in which, again, in this case, it's a more complex structure that we're going to be hydrogenating. We have on it an alkene and an alkyne, all of which are going to be brought down to a carbon-carbon single bonded species. Notice again, we have our excess of hydrogen. We have one of our metals there, this time palladium, at high pressure. So again, we're able to quickly ascertain that we are indeed going to be carrying out the hydrogenation here. So let's look at this structure that is going to be hydrogenated in a little bit more detail. So here it is, and I've drawn in, as we did before, I've sort of enunciated all of the carbons and any hydrogens attached to those carbons. Should be clear that these two structures are the same. They're just drawn in two different ways, and the structure on the bottom just has more detail in it. And the reason I'm doing that is to show where indeed we're going to be laying H2 down, and it's always onto a multiple bond. The key here is excess hydrogen. We are never going to run out of hydrogen, so all of those multiple bonds will eventually be turned into a single bond. The double bond we see there will go down to a single bond, and the triple bond, because we have an excess of hydrogen, will go all the way down to a single bond in the product. It's helpful to identify. This is certainly this structure that's being hydrogenated is an unsaturated species, but because it has, by definition, unsaturated means alkenes or alkynes. And here we have a mixture, but the question would be, how unsaturated is it? How unsaturated? Well, we can look at each multiple bond as what is called a unit of unsaturation. That double bond would have considered 1 unit of unsaturation. Because at that double bond, one of those double bonds is going to be, one of the bonds of that double bond is the original single bond. So the other one is a unit of unsaturation. So a single bond, or this double bond species right here, has 1 unit of unsaturation in it. The triple bond that we see here has an original single bond, but it has 2 others. And those are considered units of unsaturation as well, 2 units of unsaturation. I'm just bringing this up because this will become important when we are eventually dealing with other types of reactions and other substrates, or rather other reagents, where we're going to have to count the units of unsaturation. In any event, we could ask, well, if we have a total of 3 units of unsaturation on here, not that it matters, but how many H2 molecules will it take to totally hydrogenate one of these? Not that it matters, but it will eventually. Well, since we have 3 units of unsaturation on that molecule, it's going to take 3 H2 diatoms to completely hydrogenate it. Number of units of unsaturation means the number of molecules of that reagent that are going to be required to fully react with it. So let's look what happens when we put 3 H2s onto there. And those hydrogens I'm going to draw in red on the structure here, or the product here. So notice, carefully notice, where we had on the left a 1 unit of unsaturation in alkene, well, here is that H2 that added over it. And on the again on the left where we had 2 units of unsaturation, well, 2 H2s would have added over it. And that's shown here on this the way this product is drawn, sort of in a mixture of line drawing and complete bonding structure. You wouldn't have to go into this detail in the answer. Indeed, if we look in the answer box, this can be distilled down to simply a squiggle, a line drawing. It's 5, 1, 2, 3, 4, 5 carbons, all down to an alkane, and you can just draw it like that, really. The reason I'm going into so much detail here is because we're just starting out on this, and it's good to know, well, how, if we saw just specifically going from our starting material to our product, you'd be saying, well, wait a minute, that looks nothing like the starting material. How did you possibly get there? So it's helpful to go to these intermediates in order to explain how indeed we got to the given product which is in the box. Okay, time for a new reaction. A new reaction. We had gotten through hydrogenation of an alkene or an alkyne. Now we get to the halogenation of an alkene or an alkyne, and the name of the addition reaction gives us again some insight into what the reagent is. Well, it's a halogen. Look at that reagent right there, given suggestively here as X, covalent bond X. X is a halogen. And just like the halogenation of an alkane, there's only 2 halogens which fit that bill, chlorine or bromine. This is a reaction in which we have a symmetrical reagent. So if it's chlorine, well, both X's here are chlorine, Cl, Cl. If it's bromine, they're both bromine. Again, remember, halogens come as diatomic elements as well, Cl2, Br2, and again, I have drawn these suggestively. That it could be Cl2 or Br2, but written because this is an addition reaction, suggestive that, well, one of those, Cls or Brs, is going to connect, if you will, to one of the carbons, and one, by a covalent bond, to the other of the carbons. So that's it fits the same bill as we did with hydrogenation, except there it's not H2 we're dealing with. It is Cl2 or Br2 as given in this bullet point here. Now notice there is nothing over or under the arrow here, where normally we have our conditions for the reaction. When we have a situation such as this, it means that the reaction is spontaneous. It does not require anything additional. We just put an alkene in this case in the presence of Cl2 or Br2, and it stampedes over to the product profile, and it doesn't need any extra nudging, if you will. That's considered a spontaneous reaction. And the functional group interconversion here, we always have a functional group interconversion. In this case, it's an alkene to a dihalide. Let's see. So indeed, if this follows the process of an addition reaction, we have a chlorine or a bromine going to each of these carbons, and indeed that is what we get, and that double bond goes down to a single bond. Okay, let's play what's in the box. Again, here we have an alkene over here. Oh, wow, if we just, a little review, if we were going to name this one, there would be no cis trans in it because it is a terminal alkene, but we're not being asked to name this one, but it's always good to bring in some practice from these sorts of things. We have an alkene plus Cl2 as our reagent. Oh, halogen, halogenation, nothing over the arrow. Oh, spontaneous reaction perhaps, and we have a box to put in there. All of this together should tell us that this is the halogenation, in this case, of the alkene. And as we did before, I'll enunciate the two important components here. That would be the alkene. And I'm drawing in all of the carbons and the hydrogens, which we see here. And indeed, what we have here now, if we had our chlorine, Cl2, drawn in this suggestive fashion, well, we would have one chlorine covalently bonding to one carbon of that alkene, and another chlorine covalently bonding to the other carbon of the alkene, and that alkene going down to a single bonded alkane. Let's take a look at what that would give. Again, I'm trying to color code this to see how this would come out. And indeed, we see that we have chlorines covalently bonded to the adjacent carbons that once was that double bond. Indeed, we could leave it like this if we wanted to, but again, if this were in line structure, you could simply draw it as something like this. And again, this is a perfectly reasonable line structure where now we've gone down to all of the carbons, all of them are at the ends and the bends, and there are requisite number of hydrogens on each carbon to satisfy the rule of 4. That is the way we're looking at it, but indeed, this would be the line structure drawing for us to put in the box if it was asking for a specific line structure, but usually I wouldn't care. So sometimes what's in the box can throw us a curve. Now in this case we have a box which is in the place of our starting material. We're shown in this case our product. We are shown our reagent, and we're shown nothing over the arrow, which tells us it's a spontaneous reaction. So now we have to backtrack, and we have to say, all right, I have a dihalide here. That dihalide was resultant from Br2 lying down on, if you will, a carbon-carbon double bond, an alkene. So what's in the box must be an alkene. Where did that alkene originally lie on that carbon structure? It's got to be a 5-carbon structure, as we're shown here. That cyclic 5-carbon structure, well, would have to be between this and this carbon, those 2 carbons right there. And indeed, if you did that, you would write in that box, well, a 5-membered ring with a carbon double bond right there. Now notice, I wouldn't have to have my carbon-carbon double bond there. I could write as a starting material between any 2 adjacent carbons could possess that carbon-carbon double bond, and it's really all different showings of the same molecule. But it is important, at least in trying to figure out what do we put in this starting material box. Well, it has to be an alkene. Well, this is a familiar structure, at least as our starting material. We've seen this before, and it doesn't hurt to be able to use it again. We have this structure that has an alkene and an alkyne on it. Remember, we were able to count the number of units of unsaturation in there. We did that with the hydrogenation example before, but in this case, we have bromine, a halogen as our reactant, and notice I put in an excess of it. Excess bromine, meaning we're never going to run out of bromine. We have more bromine than we'll ever be able to use. Well, let me ask that same question I did before. If we have a total of 3 units of unsaturation on this starting material, which we've counted before, how many bromine diatoms, or Br2 molecules, would be needed to fully halogenate it? Well, if we have 3 units of unsaturation, just like the hydrogenation, we would need 3 diatoms of bromine, of Br2. Again, it fits together like that. So let's think about this in the case of laying down 3 diatoms of Br2 on these units of unsaturation. And what we would get out of this would be the following. And this is, in this case, this does not reduce down to a nice line drawing like the hydrogenation did. But here is one Br2. Here is the other Br2. And here is that third Br2. See if you can imagine where they laid down, between which two carbons each of these laid down, and backtrack yourself into deciding what was the original. Just pretend that original starting material is not shown there. You would be able to go back and say, okay, this would be a structure with an alkene here and the alkyne there, based upon the number of bromines that added over it. So as a product, just almost as an after effect right here, the product would be written like this if I were to go back to completely line drawing. I don't have to, but if, say, on a test or a quiz or an exam, you were asked to, well, this is how you would go about doing it. So let's look at some utility, if you will, of this addition reaction, this halogenation of an alkene or an alkyne. We'll talk about differences between the two reagents, chlorine, Cl2, and bromine, Br2. Now, chlorine is a gas at ambient temperature and pressure. It's difficult to handle. It is noxious. It's not fun to work with, adding a gas into an experiment. You have to have a closed system and such. Whereas bromine, Br2, is a liquid at room temperature. That means it's very easily measurable into a graduated cylinder or a syringe or something like that. It's much easier to work with. It's still very noxious and very nasty, but it's easier to work with than chlorine. Another interesting aspect about bromine is it is a chemical compound, at least in the organic parlance, which is very rare. It has color to it. It is colored. Bromine, the liquid, has a deep red-brown color, while most organic compounds are colorless. They're either as a clear liquid if they're in liquid form, or a colorless white powder if they're in solid form. But bromine sort of breaks that bill. So thus, bromine can be used to test for the presence of an alkene. For instance, say I had an unknown liquid, and it could be either an alkane or an alkene. How would I decide? Well, we know that an alkene will spontaneously react with bromine, whereas an alkane will not. Remember, we can do a halogenation of an alkane, carbon-carbon single bond, but we have to have intense light or heat or that sort of thing. Let's think about this. So we can tell whether a compound is an alkene or an alkane due to the uptake of added bromine. Let me paint a picture here. In the presence of an alkene, the color remains. So let's look at something. Let's say I had an unknown compound, but it was really say it was this alkene right here. This alkene is colorless. Normally, it's a liquid, I'll tell you that, at room temperature. So it's a colorless liquid. If I had a beaker of it, it would look sort of like water. And let's add a drop to that colorless liquid of very highly colored red-brown bromine, that drop. What is going to happen to that color when it hits the liquid of that colorless alkane? Well, that is going to have a spontaneous reaction. That Br2 is going to add over that double bond and form this dihalide, which is also colorless. Just because there's two bromines attached to that carbon structure does not mean it keeps its color. It is indeed colorless. So that drop going into that colorless liquid is going to disappear. It's going to go immediately colorless. Okay, hold on to that one. Let's look at the corresponding alkane, cyclohexane, which is in itself colorless. Now, what if I added highly colored bromine, one drop, to a beaker or something of cyclohexane, like we see over on the right? Well, they're not going to do that. The bromine and the cyclohexane cyclohexane are just going to giggle at each other. They're not going to react. Remember, that has to be in the presence of intense heat or intense light. So what we have is just this red-brown mixture, which we see here. We have the bromine dissolved in the cyclohexane. So that would mean if I take one drop of bromine and drop it into cyclohexane, it'll just it'll stay colored. We'll see that colored drop of bromine sort of dissolve into the cyclohexane, but keep its color. So now we have what is known as a qualitative test between, say, if we didn't know whether we had cyclohexene or cyclohexane. So, well, I know, let's take a sample of each of them and add a drop of bromine to them. Whichever one that the color disappears, that must be the cyclohexene. It must be the alkene. And the one where the color does not disappear, well, that must have been the cyclohexane. So again, we can see here this, if we did this, and in this case we have the same sort of example as before. We have bromine, beaker of bromine up top here in both cases. And if we had the cyclohexane, if that bromine were dripped, the highly colored bromine were dripped into the cyclohexane, well, that's going to stay colored as shown here. Alternatively, if we dripped molecular bromine into cyclohexene, well, immediately upon the highly colored drops hitting the liquid, that color would disappear. Why? Because it would become this colorless liquid or structure that we see over there. As we explained on the last slide, we would have this qualitative ability to determine whether we have an alkene as our unknown structure, our compound, or an alkane, by whether the color disappears or whether the color does not disappear. So we can watch this now in real time on a short video I have in here. And let me set this up for you. On the left, we have a wine glass. I don't know why they're using wine glasses in this, but we have a wine glass of cyclohexane. It's an alkane, which will not uptake that bromine. And on the right, we have a wine glass, or a goblet of cyclohexene. Notice they're both clear liquids. They both look exactly the same, but watch what happens when bromine is added to each of them. In the case of the cyclohexane, notice that bromine color, that highly brown structure, is staying. So we have that the color stays. That must be an alkane because the bromine is not reacting with it. Whereas if we splash some into the cyclohexene, immediately that color goes away. So we can say that in this case, the goblet on the right had the alkene in it, while the goblet on the left must have had the alkane in it. So there is a couple of ways that we can look at this. And in this case now it's from a quantitative sense. Qualitative means the answer is yes or no. Is it an alkene or not? Well, let's do a color test. Quantitative means, well, how much of the reagent is going to react with our unsaturated species. So the question here, how many moles of molecular bromine that we have right here would decolorize exactly 1 mole of the following starting material? And this question is actually answered much more easily than you would think. All we have to do is essentially say if we took 1 mole of this compound over on the left and we added 1 drop of bromine to it, immediately that bromine would disappear because either one of the alkenes or the alkynes would uptake it, and the color, it's not Br2 anymore, so the color would go away. But the question is how much? If I have 1 mole of my starting material over on the left, how many moles of bromine would it uptake? Well, remember when we were talking about a similar molecule, that alkene and alkyne on the same molecule, and we asked, it had 3 units of unsaturation. So how many molecules of bromine, or chlorine for that matter, would attach themselves to it? Well, if there's 3 units of unsaturation, then 3 molecules. And we could say that here. If I had 1 molecule of this, how many molecules of bromine would attach to it? Well, we'd have to find out the number of units of unsaturation on it. And indeed, if we do that, we have, well, there's 2 units of unsaturation in the alkyne, and each of the alkenes has 1 unit of unsaturation each, for a total of 4 units of unsaturation. What works on the level of the molecule works on the level of the mole. Instead of 1 molecule of this stuff, we have 1 mole of it. Well, how many moles of bromine would it take to fully brominate it or halogenate it? Well, 4, because there's 4 total units of unsaturation. We'd have 4 moles of bromine would decolorize exactly 1 mole of that starting material. Another way this could be put across is to say which of the following would decolorize exactly 3 moles of bromine. Well, it would be the one with 3 units of unsaturation. We'll go backwards through here for what would be probably obvious. Let's look at this one. How many units of unsaturation? 2. I count 2 alkenes. That's not 3. How many units of unsaturation on this one? 2, not 3. It's tempting to look at a triple bond and say there's 3 units of unsaturation, but one of those bonds on the triple bond is the original single bond. So that's 2. This one, easy. 1 unit of unsaturation. That's not 3. So all the first 3 of these that we've been looking at would not fit this bill. We need something, we need to decolor it, take 3 moles of Br2, so we need something with 3 units of unsaturation. Well, look at this one. I have 2 units of unsaturation here and 1 unit of unsaturation here. Total of 3 units of unsaturation. So the best answer in this case would be number 1. It would have to be.